Guys, we're just waiting on the technical thumbs up here. Cool. Welcome, everybody. My name is Ricardo Rivera. Some of you might know me as the maintainer for the Charger Drivers API. Also an embedded software engineer at Cirrus Logic down in Austin, Texas. And today I'm going to talk to you guys about how to charge a battery with Zephyr and kind of give a bit of a primer on what charging looks like on portable embedded systems and how to use the Zephyr charging API. So the agenda is kind of broken down into 3 sections, and I'll take maybe like one inline question at the end of each section. There'll be a big green slide. But first, I'm going to go over some fundamentals of charging and what does charging look like, the charging tree on a system. What does it look like? What is a charging peripheral? That's the device that we're interested in today, controlled by the charging API. What is a charge profile, which is the output of the charging device? And then we'll move into the good stuff, which is where does Zephyr come in all of this, and what was there before the Charger Driver API, and how that got upstreamed and mainlined into the Zephyr kernel. We'll take a look at the Charger Device API itself, as well as take a brief stop over at the battery device tree properties. And then complementary to the Charger Driver API, there is a charger sample application in Zephyr, so I'm going to walk through that charger sample application. So let's get into those charger fundamentals. So this is our system in gray, and then our Zephyr host is there in red. And on board the system, there'll be a battery pack shown in yellow. And integrated into that battery pack is the actual battery cell itself, but in parallel to it, there's typically a fuel gauge. And then external to the system is the external power. I just kind of wanted to lay out sort of the nomenclature of this system block diagram first. But now I'm going to focus in on the charger or the charger device or the charger peripheral. These terms are kind of, for the purposes of this presentation, interchangeable, but typically this will be an IC, so a dedicated charging chip, or it'll be integrated into a larger PMIC, so a power management IC. It could be a discrete circuit, but it typically isn't these days. And it kind of looks like this. So colloquially, I know that a lot of people refer to the thing that you plug into mains into the wall as the charger, but again, this is the device that lives on board the end system, and on the input side, we provide external power that can come in the form of a barrel jack with like a fixed voltage, those kind of legacy 12 and 9 volt sort of deals. It could be USB, BC 1.2, or USB PD. It could be renewables. Some really fancy charging devices have power muxes, and you can switch between the two. But generically, we provide some kind of external power into the charging peripheral that gets fed into a power converter. That power converter is driven by a state machine that is configured via a control port by the Zephyr host. On the output of the power converter, that's the power that gets sent downstream to both our system and to the battery pack. Architecturally, sometimes these are 2 separate rails, depending on what you want your charger to do. But that's what we feed here out. But focusing back in on Zephyr and the control port, what exactly are we trying to configure in this state machine? So the most important thing is the charge profile. And you may be wondering, what is it? So a charge profile is a set of instructions from the battery pack specification. So the battery pack itself will have a data sheet describing how to charge the battery safely and effectively. across a variety of conditions and kind of spell out the limits and the preferred characteristics of a charging cycle. So the charging peripheral is configured according to the given charge profile from the data sheet to produce the desired output while charging the battery. You might be asking yourself at this point, why even have an API? This sounds very set it and forget it if it's one battery pack and one charging IC. And you would sort of be right under ideal conditions, but we all know that real life is not ideal, so the charge profile is not static. And real life, the variables, the environmental variables that can play into what your charge profile looks like are things like temperature. Is it too hot or too cold to charge at the maximum capacity that this cell can take? Have the safety timers expired? Is there something strange going on? You're not seeing, the battery voltage rise. And then, finally, our external power could be the blame. So it's not necessarily the battery pack, but, the supply impedance, for example, like let's say if you have one of these very long, convenient 10-foot charging cables, that's a lot more impedance than the OEM recommended 3-foot cable. So this is what a charge profile typically looks like. This is just a generic kind of made-up charge profile that I put here that's typical of a lithium cell, which is kind of the most pertinent chemistry to the applications of Zephyr. So the colored fonts there that you see are the various currents and voltages. Those are the things that we, as the Zephyr host controller, program into the control port of the charging peripheral, and this is what we set according to the manufacturer's specifications. And then over time, as the battery charges, we step through these phases. So looking at the first phase is kind of the conditioning phase. The battery voltage is very low, so the state machine configures the power converter to sync a small conditioning current until the battery voltage rises onto a low battery voltage threshold. At that point, we have seen the battery voltage rise, and the next phase would be the charging phase, where that sunk current is stepped up to a constant charge current, and the battery voltage rises further until it hits the battery regulation voltage target. Again, this is specified by the battery pack manufacturer, and at that point, the power converter is operating in a constant voltage mode, and the sunk current is stopped and allowed to just sort of degrade in this kind of exponential way until ultimately we hit the termination current, which is just a threshold where the current going into the battery has kind of slowed down enough that we can call this battery charged and done. Going back to the block diagram here of the charger device and peripherals, the other responsibility of the Zephyr host here is to set some of the protections. So this charging peripheral, beyond, it's a kind of an application-specific power converter, so it does have some integrated protections typically. So on the output side, some of the protections we can typically set through the control port are overcurrent limiting, so setting a threshold of the maximum current that can pass into this battery pack. Similarly, battery over voltage limiting, and responding to changes in temperature that are sensed by the charging peripheral. On the input side, similarly, again, overcurrent limiting. This would be kind of like a hard comparator cutoff for your system. So it's like a true limit there. And regulation. So the difference between those two is the regulation would be like you know your supply's current limit and you see that you are approaching that limit, so you reduce your charging current in order to keep the supply steady, versus the overcurrent limiting, which is you just got walloped with current and you isolate the system because something's gone wrong. For overvoltage, a little different. Obviously, if you plug in an adapter to a system that exceeds the voltage rating for your system, you want to hit this overvoltage limit and isolate yourself from that supply. But for the flip side on the regulation, we typically set an undervoltage regulation value to prevent the external power from collapsing. So at this point, that was very hardware heavy. I'll take like maybe 1 or 2 inline questions if anybody's got one. All right. So I'm going to dive into the...
Actually, I have a question for you.
What's up?
So can you briefly explain the advantage? I've used systems where there's a charger that's kind of its own thing. It's not connected to the MCU at all. And what are the advantages of this kind of setup where you actually you can talk to the charging circuitry?
Right. So there are sort of like resistor-strapped charging ICs where you just, you place down your various whatever impedance values on a pin and you set some of those thresholds. But this, being able to talk to the charging IC itself has the advantage of being able to respond to certain events in software. So it's not just a fixed static charge profile. There's also, I mentioned it in the, right here. There's some status info and some telemetry that state machine does expose, and that could be valuable to your specific application and your charging task loop. I think that covers, cool. All right, so let's get into the fun part while you're all here. How do we do this with Zephyr? And let's talk about what was in Zephyr before and touch on the Linux power supply class. So prior to the mainlining of the charger driver API, there is no dedicated interface for facilitating a battery charging cycle. I believe there are some attempts at that in sensors, but nothing like very specific to the application. And a charging API had actually already been proposed in an RFP for the fuel gauge driver API. So if you remember back in the system block diagram, there was the battery pack with an IC on board. In Zephyr, prior to the charger driver API, there was a fuel gauge driver API RFP, and it mentioned a future need for the charger driver API. So I got to cracking on it, and I took quite a bit of inspiration from what exists in Linux. So for those of you that may not know, the way that you do all of what was aforementioned in the previous slides is in Linux, there's a power supply class that provides runtime access to both chargers and fuel gauges, as well as some boot time configuration for fuel gauges and chargers. And the charger driver API and both the fuel gauge driver API took inspiration from the power supply class with some additional tweaks for Zephyr, intentionally so that it would be familiar to anyone that's worked with the power supply class in the past. And this is what the charger driver API looks like. You can find it in charger.h. And it describes these 3 handlers. So we have a get property handler that'll grab a property value from the client driver. We have a set property handler that will set a property value from the client driver. And we have a charge enable handler that is responsible for starting and stopping the charge cycle, which is the execution of that charge profile shown before. And these are the properties that I was referring to in the get property and set property handlers. A lot of these should look familiar to anyone that's used the Linux power supply class. They almost all have the same exact names with charger prefix to it. But additionally, in Zephyr, we allowed for the properties to be extensible to allow for some custom vendor-specific properties. This is a pattern that you see kind of throughout Zephyr where there'll be various properties tied to a subsystem, and there'll be a common count, and then anything beyond the common count is an out-of-tree extension of the existing properties. So on the battery, on the device tree side of things, there's battery.yaml, which describes the static battery characteristics that should be applied at initialization. This is also inherited from battery.yaml in Linux. So we have these basic properties that are specific to the battery pack and that come from its specification. And this DT binding is shared between both the charger driver API and the fuel gauge driver API. There's no need to kind of duplicate that. So they share this common device tree code. So before diving into the sample application, maybe a quick inline question about the charger driver API itself. Going once, going twice.
Sorry, online, property online versus property online notification.
That one was added fairly recently. And it's necessary in Zephyr because of that specific comment right above the charger driver API. There it says, caching is entirely on the onus of the client. So the online notifier was added because there's a Maxim chip, and I've seen this kind of requirement in some other vendors' silicon where using the interrupt line is required, which is not super common in Zephyr. A lot of times the peripherals are just polling, but for that specific chip, you need to use an interrupt line. And that property is used to call and grab the online value in an interrupt handler, so in the ISR, and then update the cached value. Because in that driver's implementation, when you grab a property, it's just the cached value. So once you get that interrupt, you actually go grab it through that notifier. Awesome. All right. I'm going to go ahead and get into kind of a walkthrough of the sample application for the charger driver API. Right, so this sample application, for those that haven't been, for those that don't know, typically when you upstream an API or a subsystem in Zephyr, you're encouraged to have a sample application to go with it. So we went ahead and did that when upstreaming the charger driver API. And the sample application is just a simple charging task loop that's intended to show system integrators and developers how to leverage the charger driver API for their own applications. It's an infinite loop. The charging task is an infinite loop that's broken out of only when the charging cycle is complete. Inside of that task loop, there's a do while loop that's just going to poll for external power and a switch case for handling the charging peripheral status. So I'm going to go through this, put up a kind of a flow chart, and then a code snippet showing how it's kind of accomplished. So we enter the task loop, we've probed, we've initialized, and the first thing in the charging task that we ask ourselves is there power connected? If not, don't do anything, wait a while and see if there is power connected. If so, try and charge to the battery. This is what it looks like. Just grab that charger online property, and if it's offline, hop out of that infinite do while and hit the charge enable handler and try and charge a battery. So once you try and enable the charging cycle, the next thing you're going to want to do is check the status to see if you actually did end up charging. So there's 4 different ways that you can go from there. If you did end up charging and the charging device is reporting that you're charging, it's helpful to report the charge type, see what phase of that charge profile you're in. and then check it again. Again, this is just a sample application. It's not telling you how to write your own charging task loop. That's up to the developer. But this is kind of just a generic how to get through a charge cycle kind of a loop here. And so if you enable charging and you see that you're not charging, so that is to mean that there is power provided, you tried to charge a battery and you're still not charging, then something has gone wrong. So you would report the charge health property and see what you would do. So in the case of the sample application, it does nothing because it doesn't go into specifics on how to handle each possible health outcome. Some of those things are really a sign of a system error, like something's gone horribly wrong and you want to stop charging. Some of it is just, you're in kind of a warm spot and you just got to wait it out, and then you will start charging once the fault condition goes away. But in the case of the sample application, it just does nothing. It just reports it out to you and does nothing. If you're discharging, then you go back to the previous slide and you start polling for power again, because that means that the power has been taken away. The external power has been taken away, and there's nothing to do here. And then finally, if you report that the status of the charge cycle is full, then charging is done, and we return 0, and that's the end of the charger sample application. And it's kind of hard to break this switch case and keep it legible, but you can sort of see how that's done here. So I'm going to move on to closing. I don't know if there's any questions about the sample application. Cool. So in closing, some future kind of subsystem improvements for chargers in Zephyr. I'd really like to see, either me do it or the community, a generic GPIO charger driver, kind of getting back to what was mentioned previously about what if the charger doesn't have a control port. That doesn't mean necessarily that there's nothing for Zephyr to do, because a lot of these GPIO standalone charging devices have outputs that indicate, the online status. So it'll be kind of one of those power good outputs, or the output will indicate, it's too hot, it's too cold, or just a generic fault. So in the Linux power supply class, there is a generic GPIO charger driver, and I'd like to see that for Zephyr as well. Moving on to the next point, just like to tidy up the charger sample application a bit and add in more of the properties. On the previous slide, there is way more properties than what are used in the sample application. So part of it would be to kind of abstract it out, tidy it up, refactor it, and make use of as many of the properties as possible, just so that we have kind of full coverage. And a final point would be to add some support for some of the charger telemetry. There's often an ADC on a lot of these charger drivers, so the outputs of that ADC could be useful information, and that does not exist right now. But with that, any final questions?
Thanks for the presentation. Just a quick question. As the API stands at the moment, is it possible to limit the charge to, say, 85% to increase battery lifespan? It's probably to be done in consumer code, or in the code.
Yeah, so that would exist in your... So that would probably be this property right here. So you would just write a value into this in your charging task loop and limit it to 85%. Or you could start out already limited here with this constant charge current max. But this is supposed to indicate like the maximum that your system can take. And Some of the charger drivers do clamp to this value, so they'll pick it up from the DT entry, set that as a maximum, and then if you try and write in the application layer, if you try to do a system call and write something higher than that, it's going to say no way, or just clamp. But you can always do less with this property here, just in your application, and respond to. So you would want to reduce for health reasons?
It's actually the capacity rather than the charging current, so say limited to 85% of the full capacity of the battery.
So you would have to do that math on your own.
Okay,
Yeah.
Okay, all right, thank you.
And each of the properties do indicate, like the ones that are in natural units, they do have the unit suffix here. So this one is microamps. There's microvolts. I think the fuel gauge driver API has more units than that. But yeah, it was kept in these natural units as much as possible.
Hi, yeah, I was wondering how easy is it to add a custom property to this list of already available properties?
Right. So I think there are a couple examples in Zephyr. I haven't had somebody add anything like upstream some vendor-specific properties. Like that is possible. That's something that could be reviewed. There are other APIs in Zephyr that use this kind of architecture. But for out of tree, I mean, it's as easy as just starting, giving it a value after this common count. So these are all, it's an enum with numbers, and any properties that exist after the common count are free to use up until 2 to the 16, so 65535. Does that answer the?
Yeah, that's great. Thank
Cool.
you.
All right. Thank you, guys.
Hey, Jeremy, can you hear me?
I can hear you.
Excellent. So we're just getting everything dialed in on our end. I wanted to make sure your audio was coming through, sounding good.
Great. And you can see my slideshow?
Yes, we got your slides coming through. It is cropped a little bit small. Are you able to expand that at all, or is it full screen right now? Hey, that's better. Oh, no, it got smaller. Yeah, that's probably good right there. Ooh, that's even better.
Great.
Nice. And then will your camera be on for this one, or will you be doing this with just slides?
So can you see me? I'm connected on a video conferencing unit, and then my laptop is showing the slides.
Oh, got it. I
So-
think we can configure that. Let me try. Oh, there it is. Yeah, yeah. So we were on the wrong feed here. Okay, perfect.
If that's
So, yeah.
too complicated, I can change it. But
No, we've got it. We just had to dial it in on our end. So we've got your slides, we've got your video, audio sounding good. Yeah, so I think we'll just hang out here for, what's that, 10 minutes till the next session kicks off. I guess that's more like 20. We can give you a cue when we're ready to go here, and then we'll get rolling.
okay, thank you.
Thank you. Okay, Jeremy, I think we are ready to go when you are.
All right. So thank you for coming today. I wanted to just take this opportunity to go through a unit test for the ITE GPIO driver that I recently wrote before adding a new feature, because I think that it could be a useful pattern that we could copy for other tests for device drivers, which is an area of the code base which seems to have quite a lack of tests. Let's just start out with a little philosophy here. Ideally, you've probably seen this pyramid before. Ideally, we should have like a few manual tests or automated tests that run on real hardware, a greater number of integration tests that sort of check things end to end, and then what we should have the most of is unit tests, right? And why is that? Because the unit tests are fast, they're stable. We run them, we block pull requests on them in the GitHub continuous integration system. The integration testing, there are some of those, and that I would include QEMU testing in that same category. I believe those are run nightly on GitHub, but they don't actually block pull requests from coming through. And then, of course, testing on real hardware it's very good. Like, for sure that your code works. But the problem there is, it's not run automatically, so you don't get the same level of feedback. And it's very hard to test negative situations where you get error codes and such, because you can't fake out what the real hardware is doing. So that's generally why you want things in a pyramid structure. But what we have on Zephyr looks a little bit more like this right now. We have a few tests that are run on real hardware, and there's very little for unit tests. And here are some common excuses, right? And this one in bold, well, it just can't be done. There's just no way to intercept these register accesses. This is the one that I want to talk about today, because I think we've got this is a potential mechanism to do this. Where it says drivers there, if you download the slides from the schedule, that link takes you over to codecoverage.io, where Zephyr has all the coverage metrics for the various portions of the system. You'll see that things like kernel and Wi-Fi are pretty well tested, and the other things not so much. It is a little bit misleading, though, if you look at the code coverage dashboard, because it only includes, if it says like 50 out of 100 lines are covered by the tests, that 100 lines only include the files that were linked into a test. So if there's, one test and it tests one file, and there's 99 files that don't get tested, that might still show up as 100% test coverage, even though most of the files never even got compiled. So just be aware, if you're looking at the coverage dashboard, that it can be misleading. So let's dig into this case study here. So we had a desire here at Google. I guess I should have mentioned that. I'm on the Chrome OS team at Google, working on the embedded controller firmware. My focus is primarily around testing, hence the topic here of this talk. The ITE chip, its GPIO controller, does not support level-based interrupts, only edge-triggered interrupts. And we really wanted level-based interrupts. And so the goal here was, well, if we could emulate level-based interrupts in the driver, then we wouldn't have to keep implementing this over and over again with every new device that uses an ITE chip that we ship. So I went looking at this device driver to try to find, what is some technique that we could use to capture those reads and writes to the registers, so that we can actually unit test this code. And I found this macro, ECReg. This was pre-existing in the ITE code base, right? This was not something I added, but it was not used in the GPIO driver. So I went ahead and wrapped every register access, as you can see in the before and after section, with this macro. It doesn't really change anything, right? It's just doing a cast and dereference there. And potentially, it might be a little more readable if we had separate read and write macros. But in this case, I was aligning it with the code base that was already there for the other drivers for this same chip. So I just left it as ECReg. And then I created a native sim test. I tried to use the unit test driver in CMake, and that did not work out well for me. Native sim did what I wanted, which is on a POSIX system, it would include that device driver as long as it showed up in my DTS overlay. But everything else would be simulated. The unit test, if you choose that as your board type, it only then includes the files that you explicitly list in your CMake file. And so then you can't call any functions in the kernel. In this case, I wanted to use worker queues, and so unit test didn't really work for me, but native sim worked out just fine. So yeah, in my config file, I made sure this driver was enabled, and I made sure I put in an entry for a GPIO controller into my DTS overlay. Now, it depends upon an interrupt controller, so I just went ahead and used the virtual interrupt controller that you would normally use in a native sim test, and that worked fine. As for all these register values and the other settings, I just copied those from the ITE chip overlay that's used for when you're developing real code for the ITE system. And so then if this was all I did, then I would have ended up with a test that when it made GPIO calls, it would try to write to those memory addresses and it would get a segment fault, right? So the next step was just getting the thing to build, because the GPIO driver code depends upon a bunch of ITE specific headers, which are not normally in the search path for a native sim test. So I adjusted the include path to include the ITE common and the ITE 8xxx2 specific headers. That almost took care of things, except for the arch cpu.h file. I was not successfully able to import that header directly because it had a bunch of conflicting things in there. So instead, I created my own within the test, but since my include directory came first in the search path, it used my file instead of using the ITE ones. And then from there, I included a POSIX arch.h file to get most of the missing function calls that I needed. And then the IRQ connect dynamic function here, I was just unable to pull in the header that defines that function. So I declared a forward declaration for it in this file. There's probably a more elegant way to do this, but this was a way to do it. We're dealing with a situation here where we're building on POSIX, right? But we actually want to execute some chip-specific code. And so it just takes a lot of glue logic here to get these things to cooperate with one another. But fortunately, I only had to do this once, right? We could have any number of tests that could share this same structure here. But presumably you would need to do this same sort of gluing for each chipset that you wanted to do some driver-specific testing for. The next step then was I replaced that chipreg.h, which is where that ECReg macro got defined. So in my copy of it, I include the ITE version of the file. Then I replace their definition of ECReg with one that calls a function instead of just dereferencing a pointer. And then I forward declared that function, which then I provide within my test to take all those register accesses and point them at fake registers that I'm going to use later. Now, ultimately, how good is this test going to be? How realistic is it? It really depends on what kind of assertions you check in the test. GPIO drivers are really quite simple. For the most part, you do a pin config and you verify to make sure that all the registers got set as expected. There's just not a lot to it. And then here, it's kind of small, but here's my implementation of this fake ECReg function. And so for each register, I redirect it to a variable. And then when it's written to by the driver code, then I can verify that the correct side effects happened. So on the left here on the screen is a snippet from one of the tests where I call GPIO pin configure with some various flags, and then I just check the 3 registers that would normally be affected by that based on the data sheet for the chip. It is kind of important if you're writing these tests to definitely check the data sheet and not just read the code, right? Otherwise, you might put the same bug into both the test and the driver, and then you're not really testing anything. So I call pin configure. I verify that the registers got set correctly. Now we know pin configure is working. The other thing that I tried to do here is call as high-level functions as possible, right? In this case, I'm calling GPIO pin configure, not calling the specific function exported by this particular driver. And that's mostly because of the GPIO driver, the boilerplate code that all the drivers use implements this concept of a logical pin, right? And if I just called directly into the driver, I would miss that logic setting of treating active as low. So it's basically inverting the value of the GPIO on every call here because I asked it to be active low. So that's a very basic overview of the test. I did have one situation here where it was a little bit more complicated because there's one particular register that when you write to it and then you read from it, the driver code expects that whatever you wrote to the register then disappears. So in this case, since my macro doesn't actually know whether or not you're going to write to the register or read from the register, I have this flag in here, register clear GPCR before read. So on every time that register is requested, I go ahead and zero out the values, which mimics what the real register does. Because you write to it, and then when you read from it, it just reads 0. Okay, so there's some limitations here, right? As I mentioned, because my macro doesn't know if you're reading or writing, it is difficult to intercept the reads. For this particular driver, that wasn't a big problem, but I can see that how, if I was doing this in like a greenfield development where I wasn't trying to preserve existing behavior, I would definitely use two separate macros for reading and writing. The set one in the production code would just be like star register equals value, and the read one would just cast it to a const pointer and then dereference it. Versus in the test, then that would call two separate functions, one to simulate a read and one to simulate a write. The other danger here is that because all I'm doing is we call into the driver with something like GPIO pin configure, and then we look at the side effect. If you're not really careful to actually think about what scenarios are important and what side effect do we need to check, it's very easy to end up just writing your test to be the same as the code. And then you have a test that works as coded. And if anything changes in the driver, the test breaks until you make the same adjustment there. Where ideally, you'd be checking things at a high enough level of abstraction that simple refactors in the code wouldn't actually break your test. And that gives you some confidence that your refactor then had no effect like you were expecting. So yeah, I was definitely trying to be careful, not just to use the code as my guideline and go off the data sheet. There's also no emulator device in this scenario, right? This is just a unit test. If I wanted to do a bigger integration test where the GPIO usage was only a small part of it, I wouldn't be able to do that here. Now, probably that's fine for the most part because native sim has a very nice GPIO emulator that is very full featured and it works very much like real hardware does. But there could be some differences. Like, for example, ITE chips only supporting edge-based interrupts, and the native sim emulator, it will support edge-based or level-based interrupts. So you could trick yourself, which is what this diagram on the side is trying to represent, right? If you have a whole bunch of different tests, all testing things at different levels of the system, you might think, well, it's fine because I tested the driver to the hardware and I tested, some other logic down to the GPIO layer, and I tested, my high level logic against my lower level logic, and it all overlaps. So even though it's lots of separate tests, I have good confidence that it works. But if you have a gap there where there is actually no overlap, your test that's checking against the registers, might not be the same as the test that's checking against the emulator. So that's another possible way to shoot yourself in the foot and not realize it. There is definitely, we could create a way to make an emulator. It would be a lot more work. Basically, we would need to treat these macros that redirect the register accesses as basically as its own subsystem. Think of it like a memory redirection subsystem. And that you could turn on even on real hardware and to force the calls to go to an emulator instead of going to the real hardware. And then you'd be able to make a larger integration test. But I think in this case, it wasn't really necessary. Ultimately, what was my goal? I didn't want to just make a test for the sake of making a test. I wanted to have confidence that when I implemented this new feature of level interrupt emulation in the driver, that it actually worked. So I didn't have an ITE development board in order to try this out. So it wasn't convenient to try it out on real hardware. So I implemented it with 100% unit test coverage. I got to 100% unit test coverage before I implemented my feature. Then I added the feature and made sure that the new code also had 100% test coverage. And that let me verify, because I was using native sim as the board, I was able to use work queues and the various other features of the Zephyr kernel in the test, just like the driver does. And so I was able to verify that native sim has interrupt handlers. So in my test, I can say, set up the interrupt handler and then set the registers as if the interrupt was firing. And then you tell native sim, okay, trigger the interrupt for this particular interrupt, this emulated interrupt controller. And then the GPIO driver picked that up and it retried until the level went down, and it all worked just as expected in the testing. So recently, we had a brand new Chromebook launch that we were working on, and we had two devices sharing a GPIO, and it was one of these situations where it's like, oh, it sure would be convenient if we could just set this to level-based interrupt triggering. So we did, and it worked. First try. So I think this was a good success story for unit test first driver development, right? Or at least a feature development. It passed in the test, and then we tried it out on the hardware, and it worked just like we thought it would. Yeah, that's all I have. It looks like we have about 8 minutes remaining here for questions. So if someone wants to unmute the room and.
Hey, Jeremy. I was just curious.
Yes.
Would installing like a handler for the segmentation fault signal, would that have been another alternative to basically catching these memory accesses and attempting to validate them?
I think that would work. I don't know. The trouble, though, is that, like on a POSIX system, page faults are going to happen at the page level, not at the individual register level. So I think that would only let you intercept the first access unless you were explicitly unmapping the page again then after every single access.
Okay, cool. Thanks.
And what if those register addresses happened to be valid for something else? Then you would end up just overriding whatever data happened to live at that address.
Cool. Thanks.
Hi, I had a quick question on, I'm not really familiar with native sim, but when talking about GPIO drivers, obviously, outputs are driven from your code and your tests. How did you handle the input side and getting activations and that sort of thing in that environment for your unit tests?
So the unit test for testing inputs, it sets all the chip registers as if an input was coming in, the emulated registers, and then triggers the interrupt, and then the driver will read the GPIO state from the fake registers, and then we verify in the test that the correct logical value comes back.
Cool, that makes sense. Thank you.
Because ultimately a GPIO driver, right, it's just comparing a set of hardware registers with some logical state. And we don't have, it's a test, so we don't have the physical lines, but we can make those registers be in any possible state that we want to simulate and verify that the driver does the correct thing, including simulating error conditions that might never happen in real life, but we could at least see what the code would do if the registers got into those very strange situations.
Yeah, so one question I have is, did you consider if it's possible to mess with the linker, maybe actually put some symbol or section memory we control at the address of the memory app peripherals? Or is there too much risk of overlap or conflicting with something that has to be at that address?
I don't think that when you're building for POSIX, you don't get 100% control over the layout of your binary. So no, I didn't try that.
Any other questions for Jeremy? All right, I think that's it. Thank you very much, Jeremy.
All right, and yeah, download the slides on every page there. I have links in the code snippets over to GitHub where the full code is. I hope that this unit test can be a model that other people might want to copy from, and maybe it will save you a little time when trying to write your own device driver tests.
All right, thank you.